Alright guys, I'm back. Hopefully you filled these three little lines in here, three little words in here pretty quickly. If two coplanar lines are blank to the blank line. So we're starting off, the givens on this sentence are going to be a little different. So you're going to be given a right angle here, you're going to be given a right angle here, which means the adjective up here that describes the lines would be two coplanar lines, in other words M and N, are perpendicular. You'll often see the word perpendicular given by right angles on there, to the same line, in other words to the transversal. Maybe you didn't have that one before. Then the two lines are blank to each other. Well, if these are both right angles, it's very obvious how M and N relate to each other. They should be parallel. So this is a situation where there's no arrows given on here. It's kind of like how we did sections 3.2 and 3.4 were sort of sections 3.2 and 3.3 were sort of a logical switch of one another. This is the same idea. Now you're given angles. These are both 90, and of course it locks this in place and it locks these lines parallel to one another. This little sentence on your paper says explain this theorem in terms of P, M, and N. In other words, use those symbols. Use the symbols for perpendicular, parallel to describe what's happening on there. Rewrite this sentence with letters and symbols. So just to get you started on there. Oh, now I'm adding on the arrows. Maybe you don't want to add those on there. That's sort of the conclusion of it. Those won't be given when you're applying this theorem. Here's what I'm talking about for symbols. So if P is perpendicular to N, P perpendicular to N, and P is perpendicular to M, that's also a right angle there. Then your conclusion is you got parallel lines. So M is parallel to N. So it's a sentence using or statement using the symbols on there. We could prove this thing again very easily, just like we did in the last one. You know, if I put the right angles in these positions, you could prove it using corresponding angles. Probably pretty obvious. If this is 90, how much is that one? Well, duh, that one's also 90, and this one's also 90 because it's vertical to this one. If I put the right angle box here, you could have proven this using alternate exteriors instead. You know, if I were to move this inside here, you could have proven it using alternate interiors. So it's a very easy proof. I'm not going to go through a two-column proof format for it. But kind of just makes sense for what we've been studying here. And I added this on here. Why does the word coplanar have to be here? It kind of relates to what I talked about before. If you were to take, you know, it says if two coplanar lines are perpendicular to the same line. If I were to take this off of here, take M off of here, but still make it perpendicular to P. So I'm just going to rotate it so it's now pointing out at you into the screen, out of the screen, and I point it literally out of there. It's still at a right angle. If I make that at a right angle at the screen, it's still at a right angle. How would line M, which I'm holding in my hand now, relate to N? In other words, it's perpendicular to P, N is still perpendicular to P. How do M and N now relate to each other? And of course you go, oh yeah, they're skew. That's sort of why we talked about skew in the beginning of this chapter. It doesn't come up very often, but it's sort of the rare case that could disprove this theorem. If I didn't have the word coplanar here, somebody could come in and say, well, what if it's skew? What if it looks like that? This is sort of trapping you onto one surface. Alright, there are two examples. Go through the algebraic examples on here. This one's on the back of your page, so don't worry about that one right now if you don't want to. The direction says solve for x and y in each situation. I'm actually going to use x and y in this problem and then a and b in the second problem. So, and I don't think I'm going to give you any more givens on there. I'm going to have to double check on that. This one I'm giving you two right angles, the little boxes. Keep an eye out for those as you're working through problems. If you overlook that, you could just be spinning tires for a while realizing you can't solve a problem if you miss the fact there's a right angle on there. So for this one, just solve for x and solve for y. It's 5y for this angle and 2x plus y for the angle to the right of it. And then for the one on the back of your page, the angle over here is 2a minus b. Angle on the far right is a plus b. And again, you got a little box right there in the corner. Good time to pause, solve them, double check, you know, take 30 seconds to double check. I don't think these are terribly difficult. But you're going to see we're kind of coming back into the algebra sort of review or application in here. Hopefully that's one of your potential equations. Like I said, it's a good time to pause and work on your own. And of course that gets you nowhere. I'd ask the question if I was in class, why does it get you nowhere? And hopefully someone would raise their hand and say, well, you got two variables and only one equation, which means you need a second variable. So you'd have to do something with the 5y. And of course you can solve that pretty easily. You know that's 90 because it's a linear pair with the 90 next to it. and I think you should have gotten 18 for y. And this is sort of a system of equations. It's a quicker system. You know, one of them you can't solve, the other one you can easily solve. Take 18 and plug it back in for y, and now of course you can subtract from 90, divide by 2, and get a pretty simple value for x, which I'm showing there on the bottom of the screen. So it should be 36. Alright, on the back of your paper, you got this one with a and b on it. And here's one where it's maybe a more true system of equations on here. If you just say a plus b equals 90, that gets you nowhere. Now, before I put those arrows on there, this problem was impossible. You knew nothing about this second line over here. Was it a 90-degree angle? Was anything congruent on here? I just threw some arrows on there. So now this is an application of that original perpendicular transversal theorem. Whereas this one was the converse, where you have two right angles that are given on it. Same idea, same setup for the algebra on here. You've got 2a minus b has got to be 90 now, because it's a same-sided interior with this one. And same-sided interiors add up to 90, so if that's 90, that's also 90. And of course that gets you nowhere because you have two variables. The other equation, a plus b is equal to 90, because it's vertical to this 90. And I'm showing this intentionally like this. I set you up to use elimination on here if you'd like. Combine those equations, the b's should eliminate. You get 3a equals 180, and of course a has got to be 60. And I would say this is probably the easier place to plug in. If a is 60, b logically would have to be 30, because they have to add it to 90. Hopefully that makes sense. When you go on to the bottom example, I'm going to throw some stuff up here to let you work on that. You'll see you got right angle box, 2D, C plus D, and 3C plus 10. Let you have a few minutes to work on that. When you come back to the third part and the final part of this thing, hopefully you've got some solutions, some answers that you're happy with.